In bipolar transistors, we have emitter, base, collector. Okay? And for generalized base transport, what we have done is that the collector current should be equal to the emitter current Okay, this is a forward bias. This is a reverse bias. Well, what we have done to get the current, the plot that we had seen the collector current versus VBE, and we have seen that we are going to have a straight line here, right? And to deduce the collector current, we use JP is equal to 0 in the base. To get electric field existing between this emitter and the base, okay? And that is KT over Q 1 over P dP over dx. And then solving for Jn across base. Given injected electrons subject to electric field. All right, and then Jn is dPn over dx. It can be written as this, right? Then since Jn is constant across base, obviously we're neglecting recombination. Do integrals as for MOS transistors. That is Jn base P dx or Q dn is equal to base dpn. Well, Pn product is going to be equal to Pn, and the boundaries are collector base and emitter base. Okay, and we know Pn at both end at the junction, that is Ni square e to the free Be over 3t, and Ni square e to the free Be over 3t. Okay, so current is going to be the emitter area Ni square over integral base pdx over qdn. Okay, and e to the free b c over free t minus e to the free be over free t. That is the equation. Okay. And this is we call Gammel number, which is the charges in the base, the doping concentration in the base. And this is the conclusion that we're going to have in the bipolar transistors. Okay, and about the gain, we have discussed several things. Let's see. Emitter, base, and collector. And then, well, we have to think emitter and base only, right? Here, the base, emitter. And this is the space charge region. Okay, between emitter and the base. And firstly, we have for the current gain, we have 3 terms involved in the current gain, and that is firstly the injected electron is going to recombine with the holes in the neutral base. Okay, so injected minority carriers. In this case, the electron is a minority carriers in the base, and the recombination of this recombination of injected to minority carriers with majority carriers, which is a hole in the base with at base before collected at collector. That is one thing which influences the current gain. Okay. Then the second term we have thought is when we apply the voltage between the emitter and the base, not only the electron is going to be injected to the base, but also the holes now is going to be injected to the emitter, right? And we want this current, which is current between base and emitter, we want to make this thing as small as possible. So we have to calculate that BE, okay? And that is going to be injection of hole into the emitter by forward bias emitter to the base. Okay? And lastly, we have to think about the recombination in the space charge region that is happening in this neutral, in this space charge region. The electrons and holes is going to be recombined, okay, in the space charge regions. So that is a base emitter space charge region recombination. And for each of these, we had see, can you get the camera on this? Let's move it. Okay. We can deduce the base transport factor. That is alpha t, and alpha t is going to be minus reverse I N E. It can be represented like this, right? Where I N E, for example, is IS 1 minus e to the v BE over VT. That has been, we have solved this. And then IS is Q square A square N I squared D over QB, the Gamma number, right? And so alpha T is 1 minus XB square over 2D N tau N, and that is going to be 1/2 XB square Ln square, different length square. And for the second term, we had emitter injection efficiency. Injection efficiency. That is gamma, and then INE over INE plus IPE. The whole current which is injected to the emitter, and the electron current which is going to be injected to the base. So the total, the ratio of electron injection to the total, that is going to be the efficiency, injection efficiency. And then that is INE over I total. And then that is going to be 1 plus XB over XE and AB DPE and DE DNB, things like this. To have some numbers, example, emitter region width. Let's suppose we have with XE is 1.5 microns. Okay, base quasi neutral region with XP let's set is about 0.5 microns. Okay, average emitter doping NDE, let's say the NDE is about 5 times 10 to the 17th per cube. And average base doping and AB is going to be 2 times 10 to the 16th per cube. Then we can calculate the gamma on this base, okay? And then if you calculate the gamma on that example, the gamma now is going to be 1 over 1 plus XB and AB DPE over XE and DE D and B. So that's going to be 0.9973. The efficiency is very good, close to unity. Close to unity. Okay, and then the third part, the emitter-based space charge region recombination, we had an equations where we have to have JSC is going to be proportional to the e to the VA over 2 VT. Here it has to be emphasized that we have factor 2 here, right? Which is different from the former two cases. Former two cases, we just have VA over VT. We do not have 2. But in the space charge regions, since the electrons and the holes are to be combined in this space charge region, so we should have 2 here if you do the calculation. And for example, the space charge region width, which is XP, on both sides, emitter and in base, we said if that is 0.5 microns, okay? And the lifetime is about 100 nanosecond. Then JSC, space charge region current, is going to be 1.6 times 10 to the minus 19. That is Q value, and 0.5 times 10 to the minus 4 and 10 to the 10th, divided by 2 times 10 to the minus 7. And this thing is going to be 4 times 10 to the minus 7. All right? And then e to the VA over to VT. Yeah. That is going to be the current come from the space charge region recombination. So if you do the calculation of that, then let's say area is about 10 to the minus 5, and current is going to be 4 times 10 to the minus 12 e to the VA over 2 VT. That is going to be the current that you can get with this area. So if you set VA and ISC, 0.2 will give you 1.9 times 10 to the minus 10, and 0.4 is going to give you 10 to the minus 9. Okay, so if you take all those things into account, then the final figure that you can get with bipolar transistors is log current. If you plot that base emitter voltage like this, the ideal curve is going to be something like this. It's too close to. The ideal curve is going to be somewhat, that is going to be the ideal curve. But in reality, we have ISC, is space charge region recombination, which is the third part of the discussion. Okay, it goes like this because we have e to the A over 2 VT, E2 here, right? So it goes like this. So at the small voltage, at the the current is going to be increased somewhat. So beta gets bad. We call that the roll off. Okay? So as a whole, the current goes like this, and the high voltages, it has to roll off again because of the resistance, series resistance. So we have increase in here, and then a decrease in the high voltages, low voltages and high voltages, and in a wide range of emitter-based voltage, it just follows the ideal curve, exponential curve. So that's what we can summarize on the base current, okay, of bipolar transistors. In the next class, we are going to talk about the charge control model, and which can be applied for the bipolar transistors. Lastly, to wrap up the bipolar transistors characteristic, and then we're going to follow the notes that I gave you, the bipolar VLSI, integration and miniaturization and things like that. All right? And I'll prepare the handouts next. How was the trip? You look great, man. Okay. So I'll see you next week, Monday.